Hey, this is Rick, and this is another HTML5 game development tutorial using the TypeScript language. Today we are getting into some collision detection, and we are going to be, if you remember previously, we had this web game that I've been kind of working on, which is basically a little asteroids-like game. You know, we're not very far into it, but the next thing we need is collision detection. And initially I was going to do some simple circle collision detection, but then I thought, hey, this would be a good opportunity to do a deeper dive into, making some better collision detection and just demonstrating how collision detection works in general. So we're going to jump out of that and jump back here. And what I'm covering today is going to be some collisions between different circles, circles are the easiest and fastest collision detection mechanism. Basically, a circle is a center point and a radius, and you're basically doing your collision detection between two different circles, which is a very quick and dirty collision detection method. We're also doing some collision detection between line segments. So, technically a line goes on forever, so you wouldn't really need to do collision detection between lines in general. There are cases where you do, but most of the time I find myself doing collision detection between line segments if I need to. So those have a beginning point and an ending point, and you're basically looking to see if the two lines cross. And then we're doing some rectangles. So these are non-rotated rectangles, and this is also a very quick and easy way of doing collision detections, and it's very fast. So if you can do non-rotated rectangles, that's a really quick one. Now, a little slower is oriented rectangles, which is where your rectangles have some rotation on them. So they might be hitting each other kind of like that, but which can be a lot more complicated. But so this one's going to take a little more time to both code and to actually like show you and demonstrate. It's also a slower collision detection method, but you get more precision. So in that game we had our little ship, and if you wanted to do a circle collision detection, you if something comes in from the side, you're going to have this big space here that you got to cover up for, which is kind of annoying. Likewise, if you put a rectangle around that same guy, if he's like this, the rectangle's not so bad, fits reasonably well. But as soon as you rotate your spaceship, your rectangle, your unoriented rectangle gets much bigger, and you've got a big distance here again between the ship and something touching it and exploding. However, if you have an oriented rectangle like this, then you don't have nearly as much distance. There's still some gap, but there are a lot of things you could do to kind of cover that up in game development. Like if you have a nice particle system or effect that goes off here, a lot of times if the gap's not very big, nobody's going to notice. So moving on, the first thing we're going to do is figure out how to do some circle collision detection. So starting out, you have some circles here, and these two are obviously not colliding, and these two are. So the first thing you want to do is you want to draw a line between the two center points. That line segment you're going to turn into a vector, basically by subtracting the values. So you have C1 and C2. This is the center point from circle 1, center point from circle 2. So your vector here, your D vector's x value is going to be equal to C2's x value minus C1. And likewise, for the D vector's y value, it's going to be C2.y minus C1.y. So now all you need to do is get the magnitude of that D vector. So the way you do that is pretty simple. You're just using the Pythagorean theorem. So you just imagine this is a triangle here. You're going to have, you know, x squared plus y squared, you know, or a squared plus b squared equals c squared. You know, this being the hypotenuse of your triangle, that right there. So if you want to get the magnitude, all you have to do is take those two values, square them, and then add them together. So the magnitude squared of your distance is going to be equal to dx squared plus dy squared. You know, just straight up Pythagorean theorem stuff. Now, you could take the square root of this and get your distance, because what you're trying to check is the magnitude of d greater than the value for r1 plus r2, because you want to know, is this distance less than this guy plus this guy? You know, so if it is, then you know these two collide. If it's greater than that, then you know they don't. So if the magnitude of d is greater than r1 plus r2, then there's no collision, which is the case up here. But if it's less than or equal to r1 plus r2, there is a collision, which is what you got there. So rather than taking the square root of this value, we're actually just going to leave it, and we're going to square this value. And that way we end up with, you know, the same check. So you could square this side, and that is computationally faster than taking the square root. Taking the square root is actually kind of a slow process. So anyway, back to our game. We're going to cut a lot of stuff out of this. And we're going to do that basically so we can just test nothing but the collision detection today. So we don't need to be drawing any of this stuff. We can get rid of most of our keyboard inputs. We're just going to have a space bar. Basically what we're going to do is, you know, we're going to test to make sure that all our collision detection is working by just randomly drawing shapes and then seeing if they collide. So we're going to leave in our detection of the space bar. We're going to get rid of shapes. We're going to leave our vector in, and we're going to be adding to vector, I believe. But we can get rid of our bullet. And you know, make sure you save your code so that you can come back and get this stuff later, because we're going to be moving on from this point, you know, after this lesson. But I want to keep in, you know, basically the game loop and the keyboard input, and I want to get rid of just about everything else, because you know, and the initialization of the window, because this is going to be a starting point for us, because I don't want to have to redo everything. Just, you know, I want to start out with some of the basics. All right, so now we have our vector, and we have a keyboard input, and we have our game loop, you know, and we have our onload stuff. So really this is some pretty basic stuff. So now what I'm going to do is I need to find, sorry. So I need to create some sort of common interface, which I'm going to call collider, iCollider. Let me put the collider in there. And I'm also creating an enumeration so that we can keep track of the different types of colliders. So here we have what's called an enumeration. And this is basically like a list of different values that something with this type called collider can have. And what I'm trying to do is just set up a series of things to define the kind of colliders we can have. Like we can have a circle collider, rectangle collider, Rote rectangle is my oriented collider. It's basically a rotated rectangle. Lines, which are line segments. And I've got polygon in here, even though we're not going to do anything with that today. But that's one of the possible types that you'll be able to have. Then I've defined an interface for collider. So all of our colliders, you'll have to be able to do hit tests with it on another collider and find out, if those two colliders are touching each other. So the other thing we have here is the collider type, which we defined up here. So every time we define a collider, we're going to have to give it a collider type. So when we create a circle collider, we'll give it a type of circle, and when we create a rectangle collider, we'll give it a type of rectangle. And then there's a position, because every single one of these guys actually has, a position in Cartesian coordinate space. There's an x, coordinate and a y coordinate on all of these guys. So there's a vector that is the position on every collider that we're going to define. So the next thing I need to do is go grab my circle collider, and then we'll go over what that is, because that's the first thing we're going to define here. Okay, so you'll notice that I'm making a call. Basically, when we do a hit test, we're going to have to go through and look at all of these different types to see, what kind of collision is going on. Now, not all these are defined yet, so I'm going to cut all of these out. But like when the object that comes in as our second collider, if it's a circle, we have to call a collision function to determine if there was a collision and pass it to circles. Otherwise, we have to pass it, if it's a rectangle, we have to call a circle rectangle collision. But really, the only one we're doing today is circle circle. So I can get rid of all of these guys. All right, so right now we're only going to have a method for basically figuring out if there's a collision between two circles. So I've created this class called collision. And collision is basically going to be just kind of a place to hold all of my different collision functions. Because I ended up creating a whole lot of different functions representing different collisions. And so I had to put them somewhere, and I wanted to kind of house them all in the same place. So I created a class called collision, and then I've created this static function within it called circle circle. So it's a circle circle collision, and the test is going to be whether there's a collision between circle A and circle B. So this is pretty simple. So this guy up here is just calling this call to circle circle collision, passing in the object that comes in and this, which is the circle itself, is going to be calling this function within the collision class. And it's a static function, so it doesn't appear on an object. It appears on the class itself. So I don't need to create a collision object. I don't need to say, var c collision equals new collision or anything along those lines, because it's just going to be there on the collision class itself. So once again, I'm using this collision class as just a way to house, basically a single place to store all of my collisions. So this is what's happening here is exactly what we talked about. We've got a vector, and we're copying, into this vector, because this is an empty vector, we're copying in the value of the A position of this circle. So this temp vector is now become the center of circle A at this point right here, once I copy the position from A. Then after that, I'm going to subtract the position from B. So going back to what we were talking about, so this, let's say this guy is circle A, and this guy over here is circle B, So to get to D, I'm basically setting, to get to this D vector, I'm saying D equals C2, sort of. I mean, what I have to do is copy the values of C2 in, not actually set it equal to C2, because then if I change this guy, it'll end up changing that guy, and that's not what I want. So I copy the values, for X and Y from C2 into D, and then I say, you know, d dot subtract, and I'm subtracting C1 from that. And that's how I get this vector that's kind of like oriented from the origin point, you know, for x and for d. So d is like a single vector with two values. So that's how I got to that. And then I take the magnitude squared, you know, which, as I said, is basically just taking r1 plus r. Basically, it's taking x dx squared plus yx dy squared, and that magnitude squared is just returning this value right here. So then I'm just checking that against the squared value of the two different radiuses. And if it's less than that, then yeah, there was a collision. Actually, we need this to be less than or equal to. Not that that's going to make a huge difference, but, you know, if the two of them touch on one pixel, we still want the collision to happen. So if the magnitude squared is less than or equal to basically the square of those two radiuses sums, then we return true. Otherwise, we return false. So now we're going to go through and we're going to actually try and test this guy. So what I want to do is just kind of like randomly draw some circles, you know. So I'm going to grab some code that I want to tweak here. So this is going to be purely for testing purposes. So this reset circle is going to create a circle 1 and a circle 2. It's basically going to take, you know, I'm going to create a circle 1 and a circle 2 in a second here. And then this is just going through and randomly assigning shapes and sizes and stuff to it. So, you know, I'm randomly deciding a radius, and I'm randomly deciding some positions that I want to place this guy, you know, and putting them all together. So let me find. And I actually need to define circle 1 and circle 2 because I didn't do that yet. Actually, you know, I'm going to define a lot of different things right now so that we can use them later. And these guys are all for debug purposes. Because we're going to want all these guys around. Circle 1 equals new. Okay. And, you know, we're also going to want to have, right now that's just setting up the like variable definition. I haven't actually created an object with those guys yet. So let me do that inside the initialization so we make sure that all of that stuff is there. Okay, now I've got a problem, which I just realized, which is a large number of these are not yet defined. Like, I haven't defined any of the other classes. So I'm going to have to comment all those guys out, but they'll be there for later when I get to that point. And likewise, I need to comment out these guys here, because we don't have a line collider defined yet. We don't have any of our rectangle colliders defined yet. We'll get there, but I need to get them out of the way for the moment. Okay, so just ignore the stuff that's commented. That's coming later. But we just created our circle colliders, and then down here we initialize them, you know, using the new statement that you use in TypeScript. I think you use it. Yeah, you use it in JavaScript too. Never mind. But anyway, so we've created two circle colliders, and we have this reset circle circle. Should probably just say reset circles. That goes and randomly assigns values to the radius and position. So we're going to want to do that whenever we press a key. We're going to want to hit space, and we're going to want to reset those values. So we've got to go back up to the keyboard input, and here I just want to call is it reset? Do I have lowercase? Yeah, reset circles. All right, so whenever I hit the space bar, that's going to get called. So the other thing I want to do is I want to draw the circles that I just I want to actually draw the circles that I just put in there. So I need some sort of draw circle function so you could actually see the circles. So I'm going to put that guy down here under the circle collider. I'm just going to put a function, and we'll remove this. This won't be in like a final game, but once again, this is for testing purposes. So draw circle basically takes your context, begins a path, sets the stroke color to whatever you pass in, and then takes the x and y coordinates you passed in here and the radius and draws a circle. Very simple stuff. So now I just need to draw those circles every time. So in my game loop, what I want to do every time I loop through is I want to look to see, oh, I didn't want that. Copied and pasted the wrong thing. I need a circle collision. Well, you know what? I'm just going to put that back. Hold on. Okay, I'm going to have to still change this, but it's closer. All right, so we want a collision, a circle collision, not circle line. This is from a different, and we want to check to see if circle 1 is colliding with circle 2. And if so, we want to draw circle 1 and circle 2 in red. Otherwise, we want to draw circle 1 and circle 2 in blue. So let's see how this guy works. Please work. Okay, why is it showing this? That doesn't look right. But I cut all that stuff out. Okay, good. So right now it's drawing them all in red. So obviously something is wrong. Let's see what I did wrong here. Oh, I did a circle collision between circle 1 and circle 1, which of course is always going to collide. So I need to change that to circle 1 and circle 2. Let's try this again. Come on, baby, work. You can do this. All right, not colliding, not colliding, not colliding, colliding. So red when they collide, blue when they do not. So blue, blue, red, they're colliding. Okay, great. So anyway, I'm going to be posting that code out there. I'm going to be posting all of this, but let me move on to lines. Well, let me move on to rectangles next. Rectangles is a pretty simple one. Unrotated rectangles. Then I'll move on to lines. So the next thing we need to do is down here where we have our circle collider, we need to add a rectangle collider. Which I have to find. Okay. So now I've found my rectangle collider, and we'll walk through what this guy is doing. Okay, so similar situation. I'm detecting all of these different collisions. Right now, all we want is the rectangle-rectangle collision. So I'm going to have to remove all of this other stuff here. Oops. So that we're only testing for the rectangle colliding with another rectangle. And we'll put all that back later when we're covering more complex collisions. So now, back to our collision class. We don't have a rectangle-rectangle collision, so I need to put that in. All we have is the circle-circle. So I need to grab the function that I've already written to check to see if the rectangles collide. And I need to put that in here. Okay, now let me go over what I'm doing here. So, basically, the way you could tell if rectangles are colliding is if they have both an X overlap and a Y overlap. So, it's a super simple algorithm. So, right here, you have overlap on the y-axis. But there's no overlap on the x-axis. So, you know, basically, a rectangle is just defined by a point at the top corner, which is the x, y position, and a dimensional vector, which is the width and height. Okay, so really there's one vector, which I call dimension. So here's a rectangle. So we have one vector that's a position that has an x and y value, and then one vector that is the dimension, which also has an x, y value, which basically is a vector that shows you going from there to there. Well, actually, I guess technically, yeah, I guess it is that way. So that is the dimension vector, which, you know, also has an x and a y value. All right. So to determine the overlap, you have to find out what the minimum x is. So here's your minimum x for rectangle 1, and your maximum x for rectangle 1, and find out if your max x, like if the minimum x on rectangle 2 is somewhere in the middle of these two, or if the maximum x is somewhere in the middle of these two on your second rectangle, then you know that there's some overlap on the x-axis, and there isn't in this case. Now here, this is actually your maximum x because of the way your maximum y, because of the way the x and the y coordinate system works. You know, in game development, where the y equals 0 is up here, and, you know, y equals, in this case right there, is what y equals 720. So like positive y goes down. So here, you know, there's y overlap because the maximum x, or maximum y on R2 is greater than the minimum y on R1 and less than the minimum y on R2, or sorry, and less than the minimum y on R1. So basically what all that means is this point here is between these 2 points here, between this point and this point. So that basically tells you that there's some overlap on the y-axis. However, there's no overlap on the x-axis. So as soon as you find out there's no overlaps on the x-axis, you know that these rectangles do not collide. Okay, so here, this is our R1, and this is our R2, and so the first thing we do is are either this point or this point between this point and this point on the x-axis. So our x, and let's just make up some numbers here. Let's say this is 0 on the x, and let's say this is 20. This is 15, and this is 30. This is totally made up. I have no idea if that's to scale. But 15, x equals 15, is greater than 0, and it's less than 20. So we have x overlap. Now let's say that this is, up here, is y equals 0. Down here is y equals 30. And this guy here is like y equals 10. Got to get rid of the R2. And then this point on the y-axis would be something like y equals 20. So you know that this point here on the y-axis is between here and here. So you know that there's y overlap. So let me just show you how this is done in code. Hopefully all this makes sense. But you're basically looking for overlap along the different axes. So it's a pretty simple simple test. So a rectangle collision, you have your A rectangle and you have your B rectangle. So if the A's x position is less than the B's x position, then we check to see if A plus the width, this dimension x, is how wide A is. So if this is then greater than the B position, then we know that there's x overlap. So initially we set x overlap, and we're assuming that there's no overlap on x and no overlap on y, and then we start looking for overlap. So if basically if A's starting position is to the left of B's starting position on the x-axis, then we have to look to see if the rectangle's width pushes the right side of the rectangle to the right of B's x position. And if it does, then the x overlaps. The other way is if B's position, if this is not true, then that must mean that B is to the left. So then if B is to the left, then you do this similar sort of look. You say, okay, well, we know B is on the left side, the starting position, so then we look to see if the B's position plus the dimension is greater than or equal to the X position. And then you're basically just doing that same thing for Y, And then if they both overlap, then you know that they're the two of them are colliding. But if either the B or the if either the X or the Y axis is not overlapping, then they are not colliding. That's a situation like you have right here. So let me just clean this up a tad, because I have this. So that's a situation like this is a situation up here where there is overlapping on the x or on the y-axis, but not the x-axis. So R1, R2, do they overlap? If you tested the y-axis first, you'd say, do they overlap on the y-axis? And you'd say, yes, this point here is between this point and this point, and you know, you get those from that. So like if you're drawing out your XY axis like this, you know, so this point is between that point and that point. So there is Y overlap. However, on the x-axis, this point is not between this point and this point, and likewise this point here is not between this point and this point. So there is no x overlap. You know, however, as we said, I just erased that other rectangle. So on this one, let me draw my rectangle back in. R1, R2. This one overlaps on the x-axis because this guy is between those 2 points, and it overlaps on the y-axis because he's between these 2 points. So this x and y overlap. So that's fairly simple. Hopefully that all made sense. And we can let me put in some testing code just to make sure this guy works. All right, so we've got our collision in there. So if we go up here, we can change this to, let me go to rectangle. I'm gonna go grab some code. Okay. So we're going to place our game loop that's constantly doing the circle check with one that's doing a rectangle check. I've got to put rect1 back in apparently, and rect2. Oh, no, that's the rotated rectangle. I need to put you guys back in and then search for you. Okay. And here we're creating a rectangle collider at the beginning. So this is in the initialization. Oh, I need to draw a rectangle. So I'm going to just draw the rectangle. I'm going to cut and paste that code too. So this needs to go with my draw circle. This is just, all this is doing is letting us visualize it. So, you know, you're taking in X, Y, width, height, a color, and a line width. The line width isn't necessary to pass in. That's why I'm defaulting this. This for debug purposes, I had it so that I could make a wider one, but I'm not using that this time. So I'm just setting the stroke, and then I'm just using CTX rect to draw the rectangle. And I need I reset. A reset rectangle function, and all this guy is going to do, I'm going to create a reset rectangle function, bring him over, and what he is going to do is just randomly create rectangles in the same way I had done it before. Oh, no, that's not the right one. Reset rectangle. There. All right. grabbed the wrong one. Grab one we're using later for rotated rectangles. Okay, so, all this guy is doing is creating a random x and y position and a random x and y dimension to create them on the screen. And then I'll need to call this whenever I hit the space bar, just like I did for the circle. All right, so let's run this guy and see how he works. All right. Okay, so blue, since they're not colliding, red when they collide. Colliding, not colliding, colliding, not colliding. So, as you can tell here, these guys are colliding on the y-axis, or they're overlapping on the y-axis. They're not overlapping on the x-axis. Same thing here, overlapping a little on the y-axis, not on the x. Overlapping on both, because, here they overlap on x, they overlap on y. So it appears to be working just fine as far as I can tell. Yeah, that should be just fine. All right. All right, so now we're going to move on to doing some line collisions. So let me see. First thing we need to do is create a line collider. If I can find it. Come on, where are you? There you are. All right, I grab this guy. Did I put him down here? Okay, where's my colliders? Circle, rectangle, line. All right, and like before, for right now, we're only interested in lines hitting other lines. We're not going to have lines hitting anything else at the moment. We'll get there eventually. So all we need to do is to detect, on the hit test, to detect when a line is hitting another line. All right, yeah. And so all a line really is a starting point and an ending point. So there's 2 points that define. This is technically a line segment, but I'm going to call it a line because I just find it easier. So there's 2 points that define this line segment, and all we're doing here is a hit test to see if those 2 lines collide. So I go to collision. Okay, and I need line collision. Line. Come on, where's my line collision? There we go. Grab this guy. Now, that is, that's in my collision. Okay, so now I'm creating this static method in here to make sure the collision happens. I also want to make those guys, put line 1 and line 2 around, bring them around. Line 1 and line 2. All right. So let's go over what happens in a line collision. Okay, so yeah. When you're doing a line collision, and I need to be able to rotate this. So there's a couple. I need a few more functions in my vector. I need to be able to rotate my vector by 90 degrees, and I need to be able to do the dot product. And I'll need to explain the dot product a little bit better, or I'll need to explain it, period. I haven't explained what dot product is yet. Rotate 90. Okay. So the first thing I need to do is go to my vector class, need to add something that rotates a vector by 90 degrees. Now, rotating a vector by 90 degrees is actually a really fast operation, because all you're basically doing is setting the x equal to the negative y and setting the y equal to the x, and that just rotates it around 90 degrees. It's a really fast operation. So I could have used just the rotate by 90 to do that, but this just speeds that process up a lot faster, which is why we have it. It's kind of a special case that, you know, makes things a lot easier. Now I need to find my dot product. Okay, so dot product is a pretty useful little function, and it's kind of a good way to tell if both of these vectors are normalized when they come in. If both of them have are unit vectors, it's basically a good way to get the cosine. I believe it's the cosine of the angle between those two vectors. But you can also just kind of get the angle between the two vectors in general, like negative. You can get basically like how these two vectors, you know, are related to each other, and just by multiplying the two x components together and adding the two y components together, you can get a good idea of how these two vectors are related to each other in terms of direction. Now, you know, based on whether the value is positive or negative. If they're both unit vectors, the nice thing about this is it's always going to return a value from 0 to or -1 to 1 based on what the cosine of that angle is. But in order to do that, you'd have to like make sure that both this and vec were normalized to a unit vector value of 1. So if you wanted to get the cosine, you could just say this dot normalize to 1 and vec dot normalize to 1, and this would always return the cosine of the angle between these two vectors, you know, if they were normalized. Now it doesn't work out that way, but you don't always need it to. So like I used to create a separate dot product function that would just normalize both of them, but sometimes you want a little more flexibility for speed purposes than that. So if you want these two to be normalized so that you get the cosine, then you need to do it, you know, without me. But you can still get a good idea of like where one vector lies relative to the other, you know, based on this dot product. So you could tell, you know, is this vector on one side or the other? You know, is its direction in one way or the other? You know, so let's actually look at our line collisions here. So you know, here we've got a colliding two lines that collide, two line segments that collide, and you know, here we don't. So you know, the way the dot product works is, you know, if the two vectors are the same, shoot, 1 second. So basically, if the two vectors that are the same, then the dot product is going to be 1, right? Because cosine, cosine of 0 is 1. So let me draw that out if I can get my thing here. So like if one angle is this way and the other is the exact same way, you're gonna end up getting a value of 1. But if like this is for normalized vectors, so a normalized dot product. If they're at 90 degrees with each other, you're going to get 0, because if you remember, cosine is adjacent over hypotenuse. And the adjacent, if something is like, so here's your cosine of 0. So on a unit vector, this would end up being like, or in a unit circle, this would end up being 1 because there's 0 degrees. However, if you go 90 degrees, it's pointing straight up. So the x coordinate, the x value, of that, or the adjacent value, is going to be 0. So if two guys are perpendicular, two are perpendicular to each other, you're going to end up, if they're both normalized, you're going to end up getting 0. If they're going in the same direction, you're going to end up getting 1, and you're going to end up getting the cosine as you go around. So let me look at. So basically, up here, this would be like, the cosine would be like 0.5, and I think 45 degrees is what, 0.71. Anyway, so you'd get like this value that drops off, corresponding to your cosine wave, as it goes around. But we don't need to. Basically, what we need to do is, when you're trying to find out if two lines collide, you want to see, okay, here's, I got a point, like, let's take this point, and let's find out if both points on the other line are on the same side or on opposite sides. So in order to do that, you first rotate this guy, your first line. So you take this point, you find out, okay, here's a vector that I want to rotate 90 degrees. So you could subtract this value from this value. You could say, okay, here's a vector that I have, and I'm going to rotate that 90 degrees. And if the dot product of this vector here and this vector, like going from here to there, if they're both positive, that means that they're like basically within 180 degrees of each other going around this way. Because then, if you remember your cosine, it goes around like that, and then it ends up like, it ends up coming, and it ends up like basically, coming around 180 degrees and then going negative, so like this is 0, this is 0.71, this is like negative 0.5, negative 0.71. So like, if they were both going in the same direction, the value would be 1. If they're going, if they're off by 30 degrees, then it would be like 0.71. But then the value goes down to 0, like it heads, like if this angle here between this guy and this guy is greater than 90 degrees, so it could go up to 90 degrees in either direction, then you know that it's to the right. Like it's basically in that same direction. It would be, over here somewhere or over here somewhere. What you want is the other point to be on the opposite side, So you want this point to be on one side of the line. You want the second point to be on the other side of the line. So you want one value to be positive and one value to be negative. And that will end up producing a negative value if these two guys are on opposite sides of the line. And then you just do that the second time here. So you end up rotating, you take this vector, you end up rotating at 90 degrees, and then you do a dot product, and you could say, okay, well, if this point is positive and this point is negative, with that dot product, then we know that they're on opposite sides of this line, because this was the normal. Hopefully this all makes sense, but basically you're using the dot product to figure out how, like, what side of this line is this particular point fall, and you want them to be on opposite sides. So if they're on opposite sides, one will be positive, one will be negative. If you multiply those two together, they will be negative. If you have two of them on the negative side and you multiply those together, you get a positive value. So you get, if they're on the same side, no matter which side they're on, you're going to end up with a positive value. So the reason we know that this line collides with this line is because when we rotate this vector, the vector that is like the magnitude, like if we subtract this value from this value, we get like a single xy value, and we rotate that by 90 degrees. Then we can also take this point to this point and say, okay, use the dot product between these two vectors and say, okay, does the value come out positive? If it comes out positive, okay, then we want to move on to the other line, and we want to or the other point, this point, and we want to make sure that point, this angle here to this comes out negative. So the bottom line here is your first angle has to be less than 90 degrees, and the second angle has to be greater than 90 degrees. And if that's the case, you know that these 2 points are on different ends of this. They cross over this imaginary line. And then you have to do it again. Because what you have here, like if you look at this second one here that doesn't overlap, we rotate this value and we could say, okay, actually, let's start with this point here, right? So this point, if we draw a vector here, this is less than 90 degrees. So we took this point, we took this vector here, we rotated it by 90 degrees to get this, this guy right there. And now we want to find out, okay, what's the angle between, not what's the angle, we'll find out basically what's the cosine of the angle, but what's the dot product between this and this? We know that if the dot product between this and this is greater than 0, then this angle is less than 90 degrees. And then we want to take this and we want to create an angle to there, or we want to create a vector going to there, like a line going from here to here, and we want to say, okay, well, is this angle greater than 90 degrees? So that'll produce a negative dot product. So this one, the dot product of this guy and this guy is positive. The dot product of this guy and this guy is negative. So we know that this line crosses through this imaginary line right here. If you extended this line segment onto infinity, these 2 points would cross. However, you don't get the same when you take the 2 dot products from this guy. So you look at, you basically do the same thing over here, and you take the angle from here to here, and you get something positive, dot product. Okay, so you end up getting a positive dot product, but this to this also gives you a positive dot product because this is less than 90 degrees. If this point were over here, however, then you would get one positive dot product, one negative dot product, because it would be greater than 90 degrees. And this is all related to the dot product being very closely related to the cosine, of these angles. So that's basically how this works. It seems a little complicated, but it's fairly important to understand dot product and how it works, because it is so useful. Um, so if you want, look it up on Khan Academy, dot product, to get a better understanding of it. But that's how this line collision test works. So let me go back, and we're going to go. Let me go back to here, and we're going to go look at our. We're going to look at the code. So we have our line. So basically, we're starting off direction A and direction B, as the endpoints. And then for each of them, we're going to have to subtract the starting point to get that, directional value. If the distance between the two, if both of those directions, like if this thing is just a point, just exit. We're not going to bother checking if it's a point, like if we're just looking at points. So we're creating a distance vector, 1, a distance point 1. So this is the point we're checking, by copying over the starting position of A and subtracting the starting position of B. And that's, if I go back here, that's basically this line that we were talking about here. So, this is the starting position of A, this is the starting position of B, and we'd already created this vector here. We created that vector, with this direction A. So this, going back to this vector that I drew here, let me change color so I can go over things a little differently. This vector here was the direction A vector. And then this vector here, so this was distance point 1. This was direction A, that guy. And this vector, like from here to here, is distance point 2. Okay. So we're getting, this one is just the direction from the start, the start point of A to the end point of A. And then we're getting two distant points. We're getting the points between the start point of A and the start point of B, and the start point of A and the end point of B. So, and as I said, we're taking that direction and rotating it by 90 degrees, so that we could get the dot product and find out if these two guys are on opposite sides of our line. If this distance point 1 and distance point 2 end up on opposite sides of our line. So we rotate by 90 degrees, we take the dot product, and we multiply those two dot products together. And if they're greater than 0, they're on the same side of that line and there is no collision. Otherwise, we can go on and check, the next one. And basically, we do this twice. We do this for each line. And if each line crosses, each other's kind of fictional complete line, the line that extends to infinity, then, we know that there's a collision. And that's how we figure out, if there's a line segment collision. So if these dot products here, so we do the same thing again. We go back and we do it. We get a different color. We get green. So now we go back and we do it, for this guy over here, right? So we go here and we get this vector, and this becomes, our direction B. And then, then we go and we get a distance point 1 and a distance point 2, and we rotate the direction B by 90 degrees to get it out there. And then we take the dot product of this guy, and we take the dot product of this guy. And if basically, if these 2 points, this point here and this point here, are on opposite sides of this line that extends to infinity, then at that point, since we tested both of them, we know that these two line segments cross. And that's how this works. So hopefully that all made sense. Now we're going to go through and just test it and make sure everything works. So I need to go up here. So I've got a collision between two rectangles that I'm doing there, and that's not what I want. I want control. Okay. I want collision dot line. All right. So perfect. I got a line collision. All right, and the keyboard input, I want reset lines. And I believe I have to still go randomly generate some lines, because I don't think I created it. Yeah, I did not create a reset lines function yet. So I still need to do that. Okay, there's reset rectangle. I want to reset my lines. Everything working? Oh, I don't have a draw line. So I need to create a draw line function. All right. So let's see. I think we can run this now. So yeah, this is just drawing the lines. I created that, random line generator that we had. Cancel you. All right. So once again, blue if they're not overlapping, red if they are. Nope. Yep. Nope. 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 Yep. Nope. Yep. All right. So everything seems to be working just fine. Okay. Now for the really complicated one. Oriented rectangles. This one took me quite a while to understand, actually. Yeah, hopefully this will all work out. So the first thing I'm going to do is find my rotate. So I'm calling these rectangles for rotated rectangles. So first thing I need to do is grab my collider. Go paste that guy in. Okay, so circle, rectangle, line. Okay, and now I need to get rid of everything but the rotated rectangle collider. All right, so get rid of you. No, that's rectangle. Okay, so all of you. And then I'm going to need to go find the collision. Okay, so now I need to add this static function to the collision. This is just like we were doing before. Something happened. I think I lost part of my... I don't think I have my whole rectangle collider. All right, let me find collision. So I'm just going to put this at the top because that's easier. All right, so let me go back and find this collider, because I think I messed something up somewhere. I don't think I grabbed the whole thing. Oh, okay, I did not. Axis overlap, project line. Yeah, because there's a lot more stuff going on here. Okay, perfect. That's why this guy's not working. All right, so we'll go into these. The rotated rectangles have a lot more stuff going on. All right, I also have this range class that I need to add. That's basically a min-max value. There's nothing too crazy about it. It just looks to see if things overlap, and you can sort and copy and combine ranges and clamp values. So nothing too significant. I think I put him down below. All right. So now we have the ranges coming back. Okay. So let me go over, just what we have in range real quick. So there's a min and a max value. This is just an overlap test. Do the two ranges overlap, just with this min-max check on the two ranges. This is sort, so if you want to verify or just make sure that your minimum is less than your maximum, run the sort function, and if not, it'll flip them. Because sometimes when you're stuffing things in, you don't know for sure which is bigger, and then you could just run the sort. This just copies the values. If you're going to combine a range, so basically this will take the smaller minimum and make that the bottom of the range, and the the bigger maximum and make that larger than the range. And then there's clamp, and all clamp does is make sure whatever value you pass in is no less than the minimum or no more than the maximum. If it's anything between, then it just keeps the value that you had. So range is pretty simple. Okay, so the rotated rectangle gets pretty complicated. Let me go over to here, the oriented rectangle stuff that I have. So the first thing you need to know is what a projection is. So basically what it works out to is we're going to be using a technique called projection to figure out whether these guys overlap. And projection is kind of like, the best way I could describe it is just you have one vector, and when you're projecting the other vector onto it, you're creating a new vector out of this line, this, kind of like imaginary line that goes on to infinity, that's at a 90-degree angle with the vector you're projecting from. So basically it's like this. So if a really basic example would be like if I had one vector there and then another vector like here, and this is really simple, so you could see the 90 degrees, then projecting this vector onto this vector kind of makes this shorter vector like that, this guy, which makes a vector basically like that. If this guy here were longer, like say he was that long, then projecting him out would basically make this vector that much longer. So it's creating this kind of 90-degree, this basically you're making a right triangle between the line that this vector is on and the line that this vector is on, and it matters which direction you're projecting to and from. And it also it doesn't have to be, one of them doesn't have to follow any specific axis. So here you've got this this one here, this like particular, there's this smaller vector, and you're projecting a longer vector onto it. And so it has to, when you're projecting a vector that's like got a larger magnitude onto one that's a smaller, you basically have to take this guy and extend him out to the further, the further point to get your projected. So your projected vector would be this, projecting this guy onto this guy creates this. So that's how projection works. And you may be asking yourself, what can I do with that? And what you could do with it actually, some clever fool came up with this. You can use it to see where these different rectangles overlap, and if they overlap on both the x coordinate and the y coordinate, or they just overlap on one, which is really interesting. So the way it's done is you have to grab two edges that are orthogonal to each other. In other words, two edges that are 90 degrees to each other. And then you use those to basically project onto any two of these other, onto any two parallel edges on the other rectangle. And you have to do that. You have to do that for both rectangles to see. So, we have basically, we'll be doing these tests on these two, and I'll kind of try and walk you through what happens. So, like for this one, if we're projecting this blue, for this one we're like going to be projecting, the oh come on, got to get a new color here. So for this one, we're going to be projecting this blue vector, or this blue edge here, onto this guy, and you have to kind of extend these lines out so that it creates, the overlap. So in doing that, in projecting, we're projecting this green edge here. We're projecting this green edge onto this blue edge, and in doing that, you could see how the 90-degree angle, being here works. So these two guys come together here, and then they create this 90 degrees, and this projection ends up being like there, like this. I should have chosen green, so this is more clear. But when you're projecting this green line here onto this line, this blue line here, it ends up, projecting basically there, So then you find out, okay, is there any overlap with this blue edge? And there is. There's overlap there, And then you have to do the same thing for this one. So projecting like. So this guy would come up here, and this blue one would come up there, and then you'd have to find the 90 degrees so that you could like project it, and it ends up like projecting basically and overlapping like there, So it's a little complicated, but it's kind of neat. I know you're probably thinking what, but like here. And then you have to reverse it and make sure that, the other way it projects too. So here, if I were to continue this up here and, project this guy at like a 90-degree angle, he would not end up hitting here. So that this guy does not overlap. So it's really kind of crazy complicated, but it works. And, when you get it, it's kind of surprising, because honestly, at first I really did not get this. But there are several things on projection. If you don't understand what I'm talking about with projection, you can watch some. I watched some YouTube videos and some Khan Academy videos on projection and trying to figure out how this thing works. And I finally understand it. And man, it's complicated. But I'm going to walk you through what I have, and hopefully it will all make sense. So let's go down to, let me get my code up here. Okay, so we want the root rectangle Okay, root rectangle. All right, so the first thing we do is we get an edge, at 0, and then we check to see if it has an axis that overlaps with the B rectangle. So, our first rectangle, going back to this guy, our first rectangle, we're getting axis 0, which is so edge 0. So let's just say this is edge 0 right there. So the first thing we're doing is grabbing that, and then we're checking to see if there's an axis overlap with this rectangle here. So so now I have to go to axis overlap. And if there is no axis overlap, then game over. Anytime you find out there's no axis overlap, it's game over. There is basically, your guys don't overlap. So every axis has to overlap with one, every time you get one of these guys, it's got to overlap. So let's find that. All right. So to do that, we get the top and bottom edge, which are these green. This is in my little diagram here. Here's the top edge. Here's the bottom edge. So we're going to grab the top and the bottom edge. And then we're going to create a direction vector, which is, this line's position. So minus the end position. So, that basically means if we go back here, we're getting a vector that is, where is it? This vector, from here to here, by subtracting those values. All right, so then we're normalizing that direction, so basically it goes from 0 to 1. So it's purely directional at that point. And then we're, in order to get the range, we're just projecting the axis onto the direction that we have. So the axis we passed in, we're projecting it onto our direction, and all that's giving us is a minimum range, for this guy here. That's all that's doing. Let's see. So, all right. Then we're projecting the top edge onto the direction. So we're projecting, we've got this direction vector that's going here, and we've got this edge. So then we have to take that out to 90 degrees, and we're projecting this guy, onto this. So it ends up not hitting this edge. There's no overlap there in terms of this specific check that we're doing. But you have a second stab at it, with the bottom. So this would go way up here, and then you'd have to project 90 degrees from here to here, and it ends up also not hitting, in your range. So that one would be ruled out pretty quickly. But then you go through this. You go through this. So you combine the range of these two, and then actually before I before I did that, I should have combined the ranges of the two and then check to see if there's any overlap in those axis ranges, and then we basically do this more than once. And here's the project line code, which honestly, yeah, I honestly, I'm trying to think if I ever completely figured out how this works. I think I did kind of understand it. I'm trying to look at it again. I cobbled this together from several examples that I found online. One was on gamedev.net. Another was a book on collision detection that I bought. And basically I cobbled this together from a couple examples. And at first, when it was first working, I felt like I didn't fully understand it. I feel like I understand it better now. But anyway, the projecting line thing, as I said, is basically just using dot products to project one line onto another and give you a range, from here to there. So it basically tells you, in the end, you're just getting like a two-dimensional min-max when you project those lines, and you can use those values to see if your projected rectangles overlap, and if they overlap, then along both the and at first I thought it was kind of interesting that you only had to do this and this, but like projecting, as long as you project along two of your rectangle's axis, you actually have everything you need to determine if there's overlap in those ranges. So doing the other two, it's effectively the same thing. Like if I did these two instead, it doesn't really matter as long as you choose two adjacent ones on your first rectangle and two parallel ones. Like you got to choose two perpendicular ones on your two edges that are right next to each other on your first rectangle, and then on the second rectangle you just have to choose two that are parallel. But then you got to flip that when you go back. When you test the other way, then you would have to test like this and this, and on this side you'd have to test this and that, or something like that. It doesn't really matter as long as these two, like you could do this one and this one, and this one and this one, on this one and on this rectangle here. As long as your first one has two that are next to each other and the other two have two that are parallel, it all ends up working out. So let me just go through and test this guy. Hopefully that made enough sense. If not, please ask questions online or send me a tweet. I'll do my best to try and explain it. And honestly, it took me quite a while to understand what this was doing. Where is this road rectangle line? Oh, I don't know how this ended up. How did this end up getting in here? I don't remember putting this in. Alright, I'm going to get rid of you because I don't need this. This is for a later tutorial. So now I need root rectangle. Okay, so I gotta put back in my variables. This is all for testing now. Actually create instances, and then home. I need to go reset root rectangle. Well, what is this? Vector. Oh, okay. And rather than the line collision, I need to put in Okay. Draw road rectangle. I need that guy in there. Draw root. Okay. Need to put him with all my draw functions. Maybe right above draw a line. And what am I missing now? Oh. Need to actually generate. Need to generate my rotated rectangles randomly. No, not draw. What is it? Reset. All right. So, okay. Let's see how this works. All right. Not colliding, not colliding, 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 not colliding, 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 colliding. So yeah, it all seems to be working pretty well. Anyway, need to get to what happens when you want to have, a line colliding with a circle, or a rotated rectangle colliding with, a line, or any of these other ones. I got to do all the permutations in a later tutorial, because this one has gotten awfully long. So anyway, I hope you enjoyed it. Please ask questions. It's hard to go over all this stuff. It's fairly complicated, especially the rotated rectangle one. But anyway, let me know if you have any questions, and I will, as soon as I can, get to making the next one. So please subscribe.